Hello friends, so today we are going to solve the questions from modern physics, and these questions are from the year 2020, and total there are 31 questions, and all these questions are from the mains part only. Okay, and there are a few questions that will be remaining for year 2020, so this will be for part 1. Remaining question we can deal in part 2. If required, we will do also the part 3 for 2020. So first question, a plane EM wave has a frequency of 2 into 10 to the power 10 hertz and its energy density is 1.02 into 10 to the power minus 2 joules per meter cube in vacuum. The amplitude of magnetic field of the wave is close to. So we are supposed to find out the amplitude of magnetic field, and we are given that EM wave which is having a frequency as well as its energy density is given to us. So we can just use the formula for, you can say, energy density of a EM wave. Energy density of EM wave, and suppose that energy density is represented as U, then this U can be written as B naught square upon 2 mu naught, and this can be also written as half epsilon naught and E naught square. So we are only interested in magnetic field, therefore we can write that our B naught will be equal to square root of 2 times mu naught multiplied by energy density, that is our U in this case, and all these values are known to us. We simply substitute the values. We get 2 multiplied by, and mu naught is our 4 pi into 10 to the power minus 7, and our energy density is given as 1.02 into 10 to the power minus 8 and its square root. So this will be coming as 1.601 into 10 to the power minus 7, and in terms of nano Tesla we can write this as 1.1 nano Tesla. 161 nano Tesla, and the option number 2 is correct, so we can just approximate it as 160 nano Tesla. So option 2 is correct. Option 2 is correct. Next question. It states that in a plane EM wave, the direction of electric field and magnetic field are represented as k unit vector and 2I unit vector minus 2j unit vector respectively. What is the unit vector along the direction of propagation of the wave? And we know that the direction of propagation is the cross product of our electric field as well as the magnetic field. you can say our propagation direction, it is directly proportional to cross product of electric field with magnetic field. And electric field is in our k unit direction. So we have electric field in k unit direction, and we are having the magnetic field in 2i unit vector minus 2j unit vector. So 2 is our constant, we can just for the time being ignore it, and we find out the cross product of this. So we can write that our k unit vector cross I minus j unit vector. So this comes as k cross I, which will be giving us j unit vector, and then we come as k cross of our j, that will be our minus, so this will be minus of minus I, which gives us our I unit vector plus j unit vector. And we need to find out the unit vector. Therefore we can say unit vector along the direction of propagation Let us suppose that unit vector is our n unit vector. So n unit vector will be our I unit vector plus j unit vector and divided by the magnitude. So this comes as I unit plus j unit divided by square root of 2. So option number 3 is correct. Option 3 is correct. Next question. We are given the magnetic field of a plane EM wave B is equal to 3 into 10 to the minus 8 sine of 200 pi y plus ct I unit vector, where c is 3 into 10 to the power 8 meter per second is the speed of light. The corresponding electric field is. So in this question we have to find out the magnitude of electric field as well as its direction. Calculating the magnitude is quite comparatively easy. We know that our electric field E naught will be equal to C times our B naught, and this B naught is our 3 into 10 to the power minus 8. So we get C is 3 into 10 to the power 8 multiplied by 3 into 10 to the power minus 8, and this minus 8 and plus 8 goes away. We get that our magnitude will be equal to our 9 volt per meter. So therefore option 3 and 4 cannot be correct one, so only second and third. So we need to find out another direction part, and our magnetic field is along I unit vector direction. So we can say our magnetic field, it is along I unit, and from the phase part, phase is given to us as sine of can write this as k into y plus ct, and this indicates that our propagation is along minus j axis. Okay. So from here we can say that our wave is propagating along minus j unit vector. Okay. And we also know that our electric field will be perpendicular to our magnetic field, and the cross product of the two, this will be giving us direction of propagation. Direction of propagation. And we know that direction of propagation should be our minus j unit vector, and b is our I unit vector. Okay. So therefore we can write that our electric field should be along our minus k unit vector. So therefore option number 1 is correct. Option 1 is correct. Next question. We are given the electric field of a plane EM wave propagating along x direction in vacuum is E is equal to E naught j unit vector cos of omega t minus kx. The magnetic field B at the moment t is equal to 0. Okay, so we have to keep in mind that we have to find out the magnetic field when t is equal to 0. And according to the standard relationship between electric field, magnetic field, and our propagation vector, which is also called as a k unit vector, we can write that relation between electric field, magnetic field, and this k vector, in case of vacuum, we know that our magnetic field B is equal to 1 upon c k and cross E. And here this k unit vector this represents a unit vector along the direction of propagation, is the unit vector along direction of propagation. And in this particular case, this our unit vector will be equal to our plus I unit vector. Now we are simply going to calculate the cross product, and that will be giving us the direction of the magnetic field. And magnitude is quite easy to find out. So we can write that our k unit vector is our I unit vector, and our electric field is in our j unit vector direction. Therefore our I cross j will be giving us a k unit vector, and its magnitude, our one second, okay, in terms of E naught it is written, so we can say our B naught will be equal to our E naught upon C. Therefore we can write that our equation for the magnetic field in general, that will be a B naught, and we have cos of omega t minus kx, and this is our k unit vector, and B naught is our E naught by C, which can be further written as that our magnetic field B will be equal to E naught by C, and we have to find out, remember that at t is equal to 0. So we get this as cos of, and this will be kx and our k unit vector. So this will be our equation of our magnetic field. Okay, so we can just put C also. C we know is our 1 upon mu naught upon epsilon naught. So finally we get our magnetic field is equal to our E naught square root of mu naught epsilon naught cos of kx k unit vector. So this is our final answer. So we get this as E naught and we have a k unit vector. So option number 2 is correct. Two is correct. Next question. It states that the electric field of a plane EM wave is given by vector E is equal to E naught x unit vector plus y unit vector sine of kz minus omega t. Its magnetic field will be given by. So we are given that our so in this option this will be our unit vectors. Okay, these are not the, these all are the unit vectors. So in terms of our magnitude we can write that our B naught will be equal to E naught by C. Okay, so this is our magnitude. Okay, and the wave is propagating along z unit vector. Okay, so we can say that our EM wave is, let me write a direction of propagation. Direction of propagation, that is our plus z unit vector. So we can write that our magnetic field B will be equal to 1 upon C, and direction propagation is our z unit vector cross product our electric field, and electric field direction is given as x unit vector plus y unit vector. So this comes as 1 upon c z unit vector cross x unit plus y unit. Okay. And now this is quite easy. So this will be coming as 1 upon c. We have z cross x. Z cross x will be giving us y unit vector. And we have z cross y, that will be giving us minus x unit vector. Therefore, we can say that our magnetic field equation, that is our B, which can be written as our B naught, and we have sine of kz minus omega t. And if we substitute the magnitude as well as direction, this magnitude comes as E naught by c, and direction comes as, one second, yeah, and this will be our y unit vector minus x unit vector sine of k, I think this is not x, yeah, kz, this is kz minus omega t. So therefore the option will be y plus x negative. So option 3 will be correct. Option 3 is correct. Next question. Suppose that intensity of the laser is 315 upon pi. The RMS electric field in the units of volt per meter associated with this source is close to nearest integer is. So we are given the laser intensity. So we can write it as laser intensity, and let us suppose that is I. It is given as 315 oblique pi, and we have to find out the RMS value. Okay. And we know the relationship between the intensity and the peak value of electric field. We already know the relationship. So we know that our intensity I is equal to 1 upon 2 C epsilon naught and E naught square, where E naught is our peak value. And in terms of RMS, we can write this as C epsilon naught, and this comes as E RMS and whole square. Because we know that our E RMS is equal to peak value and its square root. Okay. Therefore, now it is quite simple. We can write that our ERMS will be equal to our intensity I upon C multiplied by epsilon naught and its square root. We simply substitute the values, and intensity is given to us as 315 by pi, and C is our 3 into 10 to the power 8, and our this epsilon naught is our 8.85 into 10 to the power minus 12, and this comes as whole raised to the power square root, and this can be approximately written as 194 volt per meter. So nearest integer is 194. Next question. It states that for a plane EM wave, the magnetic field at a point x and time t is given as bxt 1.2 into 10 to the power minus 7 sine of 0.5 into 10 to the power 3x plus 1.5 into 10 to the power 11 t and k unit vector. The instantaneous electric field E corresponding to B is speed of light is also given to us. So first of all, let us determine the direction of propagation. So we start with direction of propagation. And for that we are going to use the phase part or wave phase. So we can say that our wave phase, it is given as our phi, and this phi is equal to kx plus omega t. Okay, and because this part is our k and this part is our omega, and in between we have our plus sign. Okay, but the standard relationship, or we can say standard plane wave phase, is given as kx minus omega t. So we can say that our standard plane wave phase that is given as phi is equal to kx minus omega t. So for this standard phase, from here we can say that it propagates along plus x, but the phase that is given to us is our kx plus omega t. Therefore we can write that for given phase is equal to kx plus omega t. From here we can write that direction will be equal to minus of x, or in terms of unit vector we can write that this will be our minus I unit vector. So this is the direction of propagation. And we already know the standard relationship between the electric field, magnetic field and propagation direction. So we know that our electric field is perpendicular to our magnetic field. Okay. And our propagation direction is proportional, we can write, is our E cross B. So we can just, you can say, substitute and find out the propagation direction. One second. Okay, we need the direction of electric field, and magnetic field is along k unit vector. Okay, so let me put it here that our magnetic field is along k unit vector. Therefore we can say that direction of propagation is our minus I unit vector proportional, this will be our k unit vector, E unit vector cross k unit vector. From here we can write that our direction of propagation of our electric field will be our minus j unit vector. And in terms of the magnitude, we can write that our E naught will be equal to C multiplied by magnetic field, that is our peak magnitude, that is our B naught. And this can be written as 3 into 10 to the power 8. B naught is our 1.2 into 10 to the power minus 7. And this will be equal to 36 volt per meter. So therefore, we can write that the equation of electric field in terms of position x and time t will be equal to our E naught. E naught is our 36, and we can write this minus and j unit vector, and rest of the things will be same. 0.5 into 10 to the power 3 x plus 1.5 into 10 to the power 11 times t. And therefore, so we are going to have this as minus of 36 and j unit vector, so option 3 is correct. Option 3 is correct. Next question. It states that when the radiation of wavelength lambda is used to illuminate a metallic surface, the stopping potential is V. When the same surface is illuminated by the radiation of wavelength 3 lambda, the stopping potential is V by 4. If the threshold wavelength for the metallic surface is n times lambda, then the value of n will be. So we are basically having two wavelengths. Okay, for first, the stopping potential is V, and for the second, the stopping potential is V by 4. So we can say that, let us call the first wavelength as lambda 1, which is equal to lambda, and its stopping potential is, let us suppose, V1, which is equal to over V. And second wavelength, let us suppose, is lambda 2, which is our 3 times lambda, and corresponding stopping potential, let us suppose, V2 is given as V by 4. And the threshold wavelength is given as n times lambda. So we can say that our threshold wavelength, let us call this as lambda th, is equal to n times lambda. Okay, and we have to find out because we are going to use here photoelectric equation. So we can say photoelectric equation, and this gives us E times Vs will be equal to H times, or let me write this, Hc upon lambda minus phi, okay, where Vs is the stopping potential. And we have two wavelengths, so we can write that for lambda 1 is equal to lambda, stopping potential is V1, so this becomes E times V1 is equal to Hc upon lambda 1 minus phi. And sorry, not lambda 1, but okay, let me write again. So we can say this will be E times V is equal to Hc upon lambda minus phi. And here this is lambda 1 is equal to lambda. So for this is. Secondly, we can say that for lambda 2 is equal to 3 lambda, we can write this as E times V2 is equal to Hc upon lambda 2 minus phi, and this gives us E for V by 4 is equal to our Hc upon 3 lambda minus phi. Now we can just solve these two equations, and we can write that our EV upon 4 is equal to Hc upon 3 lambda minus, and we replace phi. Phi will be coming as our Hc upon lambda minus E times V. And now this is quite simple. This will be coming as minus minus will be plus, so this will be 3 by 4. So from here we can write that 3 by 4 times EV is equal to, this will be Hc and this will be 2 by 3 Hc upon lambda. Therefore we can say that our Hc will be equal to, this comes as 9 by 8 EV lambda. And threshold wavelength, we can write that lambda Th is equal to Hc upon phi. So here we just substitute our, one second, we need to find out threshold is and lambda, okay, and from here we can say our work function will be equal to Hc upon lambda Th. Therefore we can use any of the given equation and we can write it as Hc upon lambda. Let me write the equation first. So we are going to use that our phi is equal to Hc upon lambda minus E times V. That is our, for the first case. Here we substitute our this phi, we get this is Hc upon lambda Th will be equal to Hc upon lambda minus E times V, and we already know Hc is equal to 9 by 8 times EV. So we substitute it. We can write this as 9 by 8 EV lambda is divided by lambda Th will be equal to lambda, this comes as 9 by 8 EV lambda minus EV. So here this lambda goes by lambda and this comes as our 9 by 8 EV minus EV. Solving this is giving us 1 by 8 times EV, and we can write this as, on the left side we can write this as 9 by 8, and this comes as our EV lambda and this is lambda Th, and on the right side we have 1 by 8 times our EV. Okay, so here this 8 and 8 goes away, EV cancels out. Therefore we can say that our lambda Th will be equal to 9 times lambda. Okay, and it is given as n lambda. So this is given to us as n lambda. So making 1:1 comparison, we get value of n is equal to 9. Value of n will be equal to 9. Next question. It states that in a hydrogen atom, the electron makes a transition from n plus 1th level to nth level. If n is very much larger than 1, the frequency of radiation emitted is proportional to. So here we are going to start with a basic energy level equation for a hydrogen atom, and from there we are going to solve it. So we can say that energy levels of hydrogen, the basic equation is our E of n is equal to minus 13.6 n square and electron volt, and it says that the transition is from n plus 1 to nth level. So accordingly, we can find out the energy emitted by the photon during this transition. So you can say energy emitted by photon, and that energy will be difference in the energy, that is E of n, delta E will be equal to for nth level minus for our n plus 1th level. Now we can just substitute their equations. We get delta E will be equal to minus 13.6 upon n square plus 13.6 upon n plus 1 whole square, and 13.6 we can take as common. We get this as 1 upon n plus 1 whole square minus 1 upon n square, and this will be a simple mathematic calculation. Now we get this as 13.6 as it is, and taking LCM we get this as a n square n plus 1 whole square, giving us n square minus n plus 1 whole square, and we open the bracket, this comes as 13.6, and open the square also, we get this as n square n plus 1 whole square, giving us n square minus n square minus 2n and minus 1, and here minus and minus n square cancels out, so this will be giving us minus 13.6, and in between we are left with 2n plus 1 divided by n square n plus 1 whole square. We are only interested in magnitude, so let us ignore the negative sign. So we can say our delta of E is equal to 13.6, and we have this as 2n plus 1 n square and n plus 1 whole square. Now we are going to use the approximation which says that n is very much larger than 1. So we can say n is very much larger than 1. Therefore, our 2n plus 1 can be approximately as our 2n, and our n plus 1 whole square can be approximately equal to our n square. Therefore, our delta E will be equal to 13.6 2n n square upon n square, and this gives us this one of the square goes away. Okay, we are only interested in n, therefore this will be coming as 27.2 1 upon n cube. Okay. And we are supposed to find out the frequency, so we can say that our frequency, which is given as our nu, is our delta E upon h, or in terms of proportionality we can write simply it as 1 upon n cube. So option number 3 is correct. Option 3 is correct. Next question. It states that a particle is moving 5 times as fast as electron. The ratio of the de-Broglie wavelength of the particle to that of electron is 1.878 into 10 to the power minus 4. Calculate the particle mass. Mass of electron is given to us. So we are given that particle velocity is 5 times that of electron velocity. So we can write our particle velocity. Let us suppose that velocity is our Vp and is equal to 5 times Ve, and their ratio of their wavelength is also given. Therefore we can write that our particle wavelength electron wavelength ratio is given as 1.878 into 10 to the power minus 4. So we are going to start with our de-Broglie formula, and we can divide that formula into lambda wavelength, wavelength of particle as well as wavelength of electron. So we say de-Broglie wavelength which is given as lambda is equal to h upon momentum, that is mass multiplied by velocity. Therefore in terms of particle we can write this as lambda p is equal to h upon mass of particle, velocity of particle. And in terms of electron we can write say lambda e is equal to h upon mass of electron and velocity of electron. So from here we simply take the ratio. Lambda p upon lambda e is equal to, this will be coming as h upon mass of particle, velocity of particle, h upon mass of electron and velocity of electron. H and h cancels out, and this comes as our mass of electron, velocity of electron, mass of particle, velocity of particle. And we are interested in mass of particle, therefore we can just manipulate it. We can write our mass of particle is equal to mass of electron, velocity of electron and the ratio of their wavelength and velocity of particle. Okay. So we simply substitute the values, and mass of electron is our 9.11 into 10 to the power minus 31 multiplied by velocity of electron, and their ratio is given to us as 1.8 78 into 10 to the power minus 4, and we have 5 times the velocity of electron. This common term cancels out, so we get mass of particle is approximately equal to, this will be our 9.7 into 10 to the power minus 28 kgs. So 9.7, option number 4 is correct. Four is correct. Next question. When the wavelength of radiation falling on a metal is changed from 500 nanometer to 200 nanometer, the maximum kinetic energy of the photoelectrons becomes 3 times larger. The work function of the metal is close to. So in this case, we are going to use the photoelectric equation and convert that with respect to two wavelengths. So we start with photoelectric equation. Photoelectric equation, and we can write that the maximum value of kinetic energy will be equal to hc upon lambda minus phi, and we have two wavelengths, and so we can write this equation into different kinetic energy format. First will be our k1, which will be equal to hc upon lambda 1 minus phi 1. I think metal is same, so it will be phi. And secondly, we can write k2 will be equal to hc upon lambda 2 minus phi. And we are given that our kinetic energy is 3 times larger. Okay, so we are given that our k1 is 3 times k2. One second. The maximum kinetic energy photo becomes 3 times larger. Okay, k2 is 3 times k1. K2 is 3 times k1. Therefore, we can write that hc upon lambda 2 minus phi is equal to 3 times hc upon lambda 1 minus phi. Lambda 1 and lambda 2 is already known to us, and we also know the value of hc. So hc is our 1240 in terms of our electron volt. Wavelength is already in nanometer, so there is no need to change anything. So we can write this as 1240 upon lambda 2 is given to us as 200. So this becomes as 200 minus phi will be equal to 3 times 1240, and lambda 1 is our 500 minus 3 times phi. Now it is a quite simple calculation. We can get from here that 2 of phi will be equal to, this comes as our 3, this will be our one second, this is correct. So we can write this as 3 times 1240 upon 500 minus 1240 upon 200. Okay, and on the, let me take 1240 as common, so this comes as 3 upon 500 minus 1 upon 200. So the LCM will be 1000. So we get this as 2 of 5 is equal to 1240, and this will be equal to our 1000, and this will be our 52321. So we are going to have this as 1, and yes, so we can write that 5 will be equal to our 1240 divided by 2000. Now this will be approximately equal to 0.62 electron volt. I think this was only work function close to third option is correct. Option 3 is correct. Next question states that two sources of light emit X-rays of wavelength 1 nanometer and visible light of wavelength 500 nanometer respectively. Both sources emit light of same power 200 watt. The ratio of number of density of photons of X-rays to the number of density of photons of the visible light of the given wavelength is. So here we are interested in finding out the density. Okay. And we start with our energy of a single photon, that is a basic relationship, and from there we can further compute our, that is, number of photons, and then we move to our density part. So we can say that energy of single photon that is our E is equal to hc upon lambda, and we have having two wavelength. First is of X-ray, and X-ray, let us call this as lambda x, which is a 1 nanometer, 1 into 10 to the power minus 9 meters, and second one is our visible, let us call as lambda v, which will be equal to 500 nanometer. So this comes as 5 into 10 to the power minus 7 meters. Now let's find out number of photons emitted per second. Number of photons emitted per second. And that is of n, which will be equal to P divided by our energy E. And we substitute energy part, so this comes as P, and this is hc multiplied by lambda. So from here we can say that our power is same in both cases, which we can treat at constant. H and C are already constant, so we can say our n is directly proportional to lambda. Therefore we have two parts. One is our X-ray, so we can say nx will be proportional to lambda x, and we have visual part, so nv will be proportional to lambda v. So in terms of the ratio, we can say our nx upon nv is equal to lambda x upon lambda v. So already we know these values. This comes as our 1 upon 500 both are in nanometers, so it doesn't matter. So this will be coming as 1 upon 500. So this is our option 2 is correct. Option 2 is correct. Next question. It states that a particle A of mass ma m by 2 moving along x-axis with velocity v0 collides elastically with another particle B at rest of having mass mb m by 3. If both particles move along x-axis after the collision, the change delta lambda in de-Broglie wavelength of particle A in terms of its de-Broglie wavelength, that is lambda naught, before collision is. So we given particle A and particle B. Particle A is at moving, particle B is at rest. So we can write that particle A, its mass, that is our ma, is given as m by 2, and its initial velocity it is given as, let us suppose, v0. It is given as v0, we need to suppose it. And then we have particle B. Particle B, its mass is given to us as m by 3, and its initial velocity is 0. Initially at rest. And collision takes place along x-axis, and we have to find out the change in wavelength. So let us use the basic collision formula, which is based on the conservation of energy as well as momentum. We can just write the formula directly also. We know that our elastic collision formulas so after collision, let us suppose the velocities are va prime, which will be equal to mass of A minus mass of B is equal to mass of A plus mass of B multiplied by initial velocity plus, this comes as twice mass of B, and denominator will be the same, multiplied by velocity of B. And we can write this as our VB prime will be equal to twice mass of A, and we have mass of A plus mass of B multiplied by VA, and we have plus mass of A minus mass of B, mass of A plus mass of B multiplied by VB. And here let me initially at rest, so we can say that its velocity, our VB, is equal to 0, and here it is our VA. So therefore we can write our, if VB is 0, so these two terms goes away, so we are left with our only VA prime. So we can say VA prime will be equal to mass of A is our m by 2 minus m by 3 divided by m by 2 plus m by 3, and VA is our V0. So we get this will be equal to our numerator will be equal to 3, and this will be 6 m by 6, and our denominator will be 3 plus 2, so this will be 5m by 6 times V naught. Here m and m cancels out, so this comes as our 1 by 6 multiplied by 5, and this comes 6 times V naught. Here 6 and 6 also cancel out, so we get our VA prime will be equal to V naught by 5. Okay. And we are not interested in B because we are only matter with our particle A. So now we can just use our de-Broglie wavelength. So we can say that our de-Broglie wavelength, which is our lambda is equal to h upon mass into velocity, and in this case de-Broglie wavelength is given to us as lambda naught. So we can write our lambda naught is equal to h upon mass of A and its initial velocity our V naught. And after collision, let us suppose wavelength is lambda prime, which can be written as h upon mass of A and velocity of A after collision, that is VA prime. Therefore, we can substitute there mass of A is our m by 2 and VA prime we found out is our V naught by 5, and this comes as 10 h upon m times V naught. And let me write this part also. So lambda naught is equal to h upon, and we have our ma is our m by 2 times V naught. So this comes as about 2, and this we have a h upon m times V naught. Okay, and we have to find out the change in wavelength. Okay, so we got all the things, though we can see change in wavelength. Change in wavelength is equal to delta lambda is equal to over lambda prime minus lambda naught. Our lambda prime is about 10 h upon m times V naught minus 2h, and this is m times V naught, and this is equal to 8 h upon mass into velocity, and we are going to express it in terms of lambda naught, and we know that our lambda naught is equal to 2 times h upon m naught. So we can write this as 4 2h upon m V naught, and this is our lambda naught. So we get this as 4 times lambda naught. Therefore, change in wavelength, that is delta lambda, is equal to 4 times lambda naught. 4 times lambda naught, option 2 is correct. Option 2 is correct. Next question. It states that a given figure shows few data points in a photoelectric effect experiment for a certain metal. The minimum energy for ejection of electron for these surfaces. So basic graph is given to us, and the graph starts from a frequency of 5, and here the value of voltage is 0 and it goes like a linear one. Okay, and peak value is given to us a C point, that is 6, V. So we can use the photoelectric equation and solve it. So we can say that our photoelectric equation, and this we know our E times stopping potential is equal to our, here we are given frequency, so we are going to write in terms of frequency h nu, and frequency is f, so let us write it as f minus work function. And in terms of our h time frequency, we can say this will be equal to our phi plus E times stopping potential. So for point B, we can just divide the equation and we can say for point B, our stopping potential is 0, so Vs is 0 and our frequency is given as 5.5. So we substitute it and this will be giving us h into 5.5 is equal to 5.5 into 10 is power 14. So this comes as h times 5.5 into 10 is power 14 is equal to our work function phi. So here we can find out easily about phi. H we know is our 6.6 into 10 is power minus 34 multiplied by 5.5 into 10 is power 14 and whole divided by our, okay, we write in this electron volt, so this will be our 1.6 into 10 is power minus 19 electron volt. So this gives us that work function phi is equal to 2.27 electron volt. So we get this as option number 2 is correct. Option 2 is correct. Next question. It states that in the line spectra of hydrogen atom, the difference between the largest and the shortest wavelength of the Lehman series is 304 angstrom. The corresponding difference for the Paschen series in angstrom is. So we are going to use Rydberg formula and accordingly adjust it for Lehman series as well as the Paschen series. So we can say that Rydberg formula which is our 1 upon lambda is equal to our R, and we have this as 1 upon n1 square upon 1 upon n2 square, where n1 is the lower level and n2 is the upper level. And with terms of the wavelength, it shows that the largest and the shortest. Okay. So for Lehman series, the lower level, that is n1, is fixed, which is our 1. You can say that Lehman series it gives us that value of n1 is always 1. And according to the wavelength, first wavelength it states is for largest, so we can say that for largest wavelength our n2 will be equal to 2 and it transition to our n1 which is equal to 1. Therefore we can write that our lambda max, 1 upon lambda max is equal to our r, and this is 1 upon 1 square minus 1 upon 2 square. This comes as 3 upon 4 times r. And now we are having our shortest wavelength. Shortest wavelength, and for that value of n2 will be our infinity. Value of n2 will be infinity and it transitions to value of n1 is equal to 1. Therefore we can write that 1 upon lambda minimum will be equal to our r, and this comes as 1 upon 1 square minus 1 upon infinity. This gives us our r, and difference in this wavelength is given to us as 304. So we are given that difference in wavelength, that is our lambda delta L, is equal to lambda max minus lambda mean, which is our 304. And we simply substitute the values. We get that our delta lambda L for Lyman series, let me write it as LS, Lyman series, maximum is our 4 by 3r minus minimum is our 1 upon r, and this comes as our 3r will be our LCM. This comes as 4 minus 3, this will be 1, and this will be equal to 304 angstrom. Now let us do the same calculation for our Paschen series. For Paschen series, the lower, that is our n1, is always equal to 3. So we can say Paschen series n1 is always equal to 3. So first wavelength is the largest wavelength. Largest wavelength, which starts for n2 is equal to 4 and moves to our n1 is equal to 3. So in this case, let us write that 1 upon lambda max, in this case let us write it a prime, will be equal to r, and this comes as our 3 square minus 4 square, giving us 7 upon 144 times r. And next is our shortest wavelength. Shortest wavelength, which gives us that value of n2 will be infinity, and it makes a transition from n1 is equal to 3. So we get this 1 upon lambda minimum prime is equal to our r. This becomes our 9 minus 1 upon infinity, which gives us r upon 9. And the difference, you can say difference in wavelength let us call this as lambda, delta lambda Paschen series will be equal to lambda max prime minus lambda minimum prime, and we substitute it, we get this as delta lambda ps is equal to lambda max is 144, and this comes as 7r minus r upon 9 upon r, sorry, and 7r is our LCM, and this will be coming as our 81. So now we are going to compare our, or we can simply take the ratio. That is our number delta lambda Paschen series, delta lambda Lehman series. This giving us 81 upon 7r and divided by 1 upon 3, 1 by 3r. And here r and r cancels out. This comes as 81 upon 7 multiplied by 3, which is approximately equal to 34.71. But we also know that our difference of this Lehman series is also given as 304. So we can easily substitute it and get the answer. Therefore, we can say that delta lambda Paschen series is equal to delta lambda Lehman series multiplied by 34.71, which comes as 304 multiplied by 34.71, and this can be approximately equal to 10550 angstrom. So in angstrom it is 10550. Next question. It states that in a photoelectric effect experiment, the graph of stopping potential V versus reciprocal wavelength obtained is shown in the figure. As the intensity of incident radiation increased, we have to find out what happens to the slope of the graph, how it is changes. So let us start with the photoelectric equation. Photoelectric equation, which gives us E times Vs, that is stopping potential, is equal to Hc upon lambda minus phi. And specifically in terms of the, you can say, equation or slope equation, we can write it as E times Vs is equal to Hc multiplied by 1 upon lambda. Okay, 1 second, this is E will be here, and this comes as a phi upon E. So this is our E is y is equal to, or we can write it in form of intercept form. Okay. So this portion will be the slope, and this portion will be representation of intercept. inclusive the negative sign. So let me write this negative and this is with a minus sign. Now we have to understand the effect of intensity. So we can say effect of intensity. Effect of intensity. So as intensity is going to increase, the number of emitted electron, or we can also say current, increases. So we can write that if our intensity increases, this results in number of electrons also increases. Number of electrons are basically nothing but our current. Okay. But this does not affect the maximum kinetic energy. Okay. So we can say from here, but this does not affect the maximum kinetic energy. Therefore, we can say that the graph does not change. Okay, a straight line does not change. So option 2 is correct. Option 2 is correct. Next question. It states that a particle of mass 200 collides with a hydrogen atom at rest. Soon after the collision, the particle comes to rest and atom recoils, goes into its first excited state. The initial energy of the particle is n by 4. The value of n is. So we are given collision. So obviously we are going to use the energy conservation as well as momentum conservation. So first of all, let's write what are the things given to us. We are given particle mass, let us call this as mp, and this mp is our 200, and hydrogen atomic mass we already know, so we can say H atom mass, let us call this as our mh, and this is, it is given as 1 GeV c square, or we can write this as our 1000 mega electron volt c square, okay, because this particle is given as in terms of mega c square, and initially we are given that hydrogen is at rest. So we can say that our initially is at rest is initially at rest, and we can say that after recoil it goes into first excited state. We are given that our hydrogen recoils to first excited state. So based on this, we can write that its excitation energy will be equal to 10.2 electron volt, and it also gives that after collision particles comes to rest. after collision particle is at rest, and initial kinetic energy is given as n by 4. Initial kinetic energy is given as n by 4 electron volt. From here we are going to find out value of n. So we are going to use conservation of energy as well as momentum. Energy and momentum conservation so we can say that momentum of particle initially is equal to momentum of hydrogen final. Okay, because initially the particle was at rest and finally the particle was at rest and initially hydrogen was at rest. So we can write that mass of particle multiplied by velocity of particle will be equal to mass of hydrogen multiplied by velocity of hydrogen. Now we can find out the recoil kinetic energy of hydrogen. Recoil kinetic energy of hydrogen. Let us call this as K recoil will be equal to half mh Vh square, and we can substitute value of Vh. We get this as K recoil will be equal to half mh, and Vh can be will be equal to over mp Vp divided by our mh whole square. So this will be equal to our mp square Vp square and 2 times mh. And we are also given initial kinetic, or we can write the equation for initial kinetic energy of the particle. You can say that initial kinetic energy of particle, let us call this as K initial, will be equal to half mass of particle and velocity of particle ka square. And we can express the recoil energy in terms of particle energy, okay, because we already know the relationship. Okay, because K recoil is also in terms of particle and K initial is also in terms of the particle velocity. So we can, let me modify it here only. This can be written as our mp upon mh, and this will be over half mp Vp square. So we get this as K recoil will be equal to our mp mh multiplied by K initial. Now we can use energy conservation. energy conservation, we can write that our K initial is equal to energy into excitation plus K recoil, and this can be written as energy of excitation plus K recoil. We already found out it is our MP MH, and this is our K initial. So we can just make minor adjustment. We can say that our K initial is equal to 1 minus MP upon MH is equal to energy of excitation. Therefore, we get this as K initial is equal to energy of excitation 1 minus MP upon MH. Now we just substitute the values. This comes as 10.2, 1 minus, this is about 200 and this is about 1000. So this calculation will be giving us 12.75 electron volt. But we are given that the initial kinetic energy is given as N by 4 is equal to 12.75 electron volt. So value of N will be approximately equal to 51. So value of N is about 51. Next question. It states that the surface of a metal is illuminated alternately with photons of energy E1 4 electron volt and E2 2.5 electron volt respectively. The ratio of maximum speeds of photoelectron emitted in the two cases is 2. The work function of the metal is. So we are given 2 photon energy and their ratio of their maximum speed. So we are going to use photoelectric equation. Photoelectric equation, and which gives us that the maximum value of kinetic energy is equal to energy of photon minus work function, which can be also written as half m v square, and this velocity will be maximum. Okay. And we are given, we have two cases. First is of E1. So we are having our E1 is equal to 4 electron volt. Let us suppose the corresponding velocity is our V1, and we have our E2. This is our 2.5 electron volt, and the corresponding velocity is, let us suppose, our V2. So we are given as V1 upon V2 is given as 2. So we can write V1 square upon V2 square is equal to 4. Therefore, we can write that in terms of the kinetic energy, this can be further written as our 2 times K1 divided by mass m, and this comes as 2 times K2 divided by mass m. Here this 2 m and m cancels out, and this comes as K1 upon K2. And K1 upon K2 will be giving us our E1 minus phi and our E2 minus phi. And this ratio is equal to 4. Now we can find out our, solve this. So we can write this as our E1 minus phi is equal to 4 times E2 minus 4 times phi, and we get this from here. 3 phi is equal to 4 E2 minus E1, and E2 is our 2.5, so this comes as 4 into 2.5 minus E1 is our 4. Therefore we can say that our phi will be equal to, this comes as 10 minus 4, that is 6 upon 3, giving us that our work function is equal to 2. I think this was, yeah, work function is about 2. Next question. It states that an electron, a doubly ionized helium, and a proton are having same kinetic energy. The relation between their respective de-Broglie wavelength will be. So we have to find out the order, how their wavelength, de-Broglie wavelength will be ordered. So we start from the de-Broglie wavelength equation only. So we know that our de-Broglie wavelength which is our lambda. So this lambda is equal to h upon momentum p, or we can write this as h upon 2m square root of k in terms of kinetic energy. So all these particles are having same kinetic energy. 2 is already constant, h is also constant. Therefore we can say our lambda is inversely proportional to square root of m. And we have electron, helium, as doubly ionized helium, as well as proton. So we need their order, so let's write them in the form of the ratio. So we can say that our wavelength of electron, proton, as well as our helium will be equal to 1 upon mass of electron, 1 upon square root of mass of proton, and 1 upon square root of mass of helium, which is approximately equal to 4 times mass of proton. Okay. Therefore we can write that this will be equal to 1 ratio square root of mass of electron divided by mass of proton, and by 2 square root of mass of electron divided by mass of proton. And from this order we can clearly see that our wavelength for our electron will be greater than wavelength for our proton is greater than wavelength for our doubly ionized helium. Therefore option 3 is correct. Option 3 is correct. Next question. It states that the time period of revolution of electron in its ground state orbit in hydrogen atom is 1.6 into 10 to the power minus 16 second. The frequency of revolution of electron in the first excited state is. So here we are going to use our formula for the Bohr radius and the time period of revolution. So we know that Bohr radius is given as our R of n is equal to n square multiplied by R1. and this is for our nth orbit. Okay, so this is for our nth orbit. Similarly, we can write velocity. Our v of n is equal to v1 upon n, and time period t of n is equal to 2 pi r of n divided by v of n, and all this for r of nth orbit. And we can write this t of n in terms of t1. So we can say our t of n is equal to, we have this as 2 of pi, r of n is our n square multiplied by r1, and v of n is our v1 divided by n. So this comes as our 2 pi r1, and this will be our n cube divided by v1. And let me write it this way. Let us divide this part by v1, and this is nothing but our t1. So this will be equal to t1 times n3, and it says the first excited state, so value of n is equal to 2. First excited state, value of n is equal to 2. Therefore, t of 2 is equal to 2 cube t of 1, that is 8 times t of 1, which gives us 8 into 1.6 into 10 to the power minus 16. So we get this will be approximately equal to 1.28 into 10 to the power minus 15 seconds, and we have to find out the frequency. So we can say that our frequency f is equal to 1 upon t, or here t is the representation of t2. This is 1 upon 1.28 into 10 to the power minus 15, approximately 7.8 into 10 to the power 14 per second. So option number 3 is correct. Option 3 is correct. Next question. It states that a beam of electromagnetic radiation of intensity 6.4 into 10 to the power minus 5 is comprised of wavelength lambda is 310 nanometer. It falls normally on a metal, work function phi as 2 electron volt, of surface area 1 centimeter square. If 1 in 10 to the power 3 photon ejects an electron, total number of electron ejected is 1 second is 10 to the power x. Then we have to find out the value of x. So here we are given as intensity, and intensity is 6.4. Okay, so we can say that intensity I is equal to 6.4 into 10 to the power minus 5, and this is centimeter square. So let us convert into meter square. So this comes as 0.64 watt per meter square. Wavelength etc. are already given to us. So we start with the energy of one photon. energy of one photon, that is our EP, is equal to hc upon lambda, which comes as 1240 divided by 310, approximately 4 electron volt. So we convert this into joules. So we get our EP is equal to 4 into 1.6 into 10 to the power minus 19. This will be equal to 6.4 into 10 to the power minus 19 joules. And we are going to find out total energy per second, power, we can say basically power falling in metal. So we can say total energy incident per second. And which is nothing but P is equal to intensity multiplied by area, and intensity is our intensity was 6.4 into 10 to the power minus 5, and area is also in centimeter square, so we leave it as it is. And so we get our P will be equal to 6.4 into 10 to the power minus 5, and total energy per second. Oh, just calculate. Now we can find out number of photons incident per second. Number of photons incident per second. Let us call this as NP. NP will be equal to P divided by energy of photon, EP. P is our 6.4 into 10 to the power minus 5. EP is our 6.4 into 10 to the power minus 19. Approximately 1 into 10 to the power 14 photons per second. And it is efficiency is indirectly given to us, that is 1 in 10 to the power 1000 photons ejects 1 electron. So we are given that efficiency is 1 in 1000 photon eject an electron. Therefore, we can say that number of electrons Ne will be equal to number of photons divided by 1000, which comes as 1 into 10 to the power 14 divided by 10 to the power 3, giving us 1 into 10 to the power 11 electron per second. And this is given to us as, let me write it here, Ne we got as 1 into 10 to the power 11, and this is given as 10 to the power x. Therefore, value of x is equal to 11. So value of x is 11. Next question. It states that an electron of mass m and a proton having same energy E in the range of few electron volt, the ratio of de-Broglie wavelength associated with electron and the wavelength of the photon is. we have to find out their ratio. So we start with the photon energy and move forward. So we can say our photon energy which is our E, and it will be our hc upon lambda photon. So from here we can write that lambda photon will be equal to hc upon E, and de-Broglie wavelength for electron de-Broglie wavelength of electron, we can write that our lambda E is equal to h upon mass into velocity, and we can write velocity in terms of energy also. So we can say our half m v square is equal to energy. So from here we can say our velocity v is equal to twice E upon m square root. So therefore we can write this will be equal to our h upon mass m square root of t 2e upon m. So we get that our lambda E is equal to h upon 2m E and its square root. So we have our de-Broglie wavelength, photon energy as well as de-Broglie wavelength. So we take their ratio. So we can see our ratio, which will be our electron photon is equal to h upon square root of 2 mass in electron divided by hc upon E, and this h and h cancels out. This will be equal to our E upon square root 2me, and this is multiplied by c, and we can just manipulate it, and this can be written as 1 upon c square root of E upon 2 times m. So this is our 1 upon E square root of E upon 2m, E upon square root of E. Option 2 is correct. Is correct. Next question. It states that when a photon of energy 4 electron volt strike the surface of metal A, the ejected photoelectrons have maximum kinetic energy Ta electron volt, and de-Broglie wavelength is lambda A. The maximum kinetic energy of photoelectrons liberated from other metal B by a photon of energy 4.5 electron volt is Tb is equal to Ta minus 1.5 electron volt. If de-Broglie wavelength of these photoelectrons is lambda A is equal to twice lambda A, lambda B is equal to twice lambda A, then the work function of the metal B is. So we start with our photoelectric equation. which gives us that the maximum kinetic energy is equal to energy of photon minus work function. And we have two metals, and kinetic energy is okay. Here the maximum kinetic energy is given as in terms of TA. Therefore we can say for metal A, we can write this as our TA is equal to our EA minus phi. EA is given as phi A, EA is given as 4 minus phi A. And we have metal B, which is our TB is equal to our EB minus phi B, which comes as 4.5 minus phi B. And we are given that T relationship between TA and TB is also given to us. So let's use the de-Broglie wavelength equation. So we know that de-Broglie wavelength, which is our lambda, will be equal to, in terms of kinetic energy, we can write this as our H upon 2 times m times k. Let's write this as k max. So everything is constant here except the kinetic energy. Therefore we can write our lambda is inversely proportional to square root of k max. We have metal A and metal B, and their wavelength relationship is also given to us. We are given that lambda B is equal to twice lambda A. So lambda B is equal to twice lambda A. Therefore, and we can also say that our lambda A is proportional to square root of TA, and our lambda B is proportional to square root of our TB. We can find out the ratio. We can say that our lambda B upon lambda A will be equal to 1 upon square root of TB, 1 upon square root of TA. This gives us that square root of TA upon square root of TB, and their ratio is our 2. So this comes as 2. From here we can say our TA upon TB is equal to 4. Or we can simply write that our TB is equal to TA upon 4. But we are given that our TB is equal to TA minus 1.5. So we substitute it, we get this as TA upon 4 is equal to TA minus 1.5. And this is quite simple now. We can write that our TA by 4 minus TA will be giving us 3 by 4 TA. So this comes as 3 by 4 times TA is equal to 1.5. This gives us that the value of TA is equal to 0.5 electron volt. And from here we can say our TB is our 0.5 TB is equal to 4, or we can say TB is equal to TA by 4, so 0.5 divided by 4. And one second, sorry, this TA will be coming as 2 electron volt. So we have our, this is our 2 electron volt. and this TB is equal to 0.5 electron volt. Therefore, for metal B, you can say for B, work function phi B is equal to energy of photon minus T of B. 4.5 minus 0.5 is equal to 4 electron volt. Option 3 is correct. Option 3 is correct. Next question. It states that the number of alpha particle deflected in a Rutherford's alpha scattering experiment varies with the angle of deflection. Then the graph between the two is best represented by. So this is directly based on the formula, and that is our Rutherford scattering formula. Rutherford's scattering formula, and this gives us differentiation of cross-sectional, you can say differential cross-section for our alpha scattering d sigma by d is equal to 1 by 4 pi epsilon naught, and this comes as 2 z multiply by small z, and we have this as e square divided by 4e whole square multiply by 1 upon sine square theta by 2. And let me write the notations. First is the derivative function, and this is called as a probability of scattering into a solid angle. Probability of scattering into solid angle. That angle is our d of ohm, and capital Z is our atomic number. Atomic number, and this small z is our charge on alpha particle. Charge on alpha particle, and E is the kinetic energy of the alpha particle. E is our kinetic energy of alpha particle, and theta is our scattering angle. Scattering angle. So from here we can, because we are only interested in the angle, therefore we can write that n of theta is proportional to 1 upon sine of 4 theta by 2. So with respect to this graph, first value of n we can take as 0, first value of theta we can take as 0. So let us consider that for small angle for small angles, theta is approximately equal to 0. If theta is approximately equal to 0, we are not, let me write this power something like this, whole raised to power 4. So for the time being, we can just ignore the power also. And when theta is equal to 0, the sine of theta by 2 can be approximated as theta by 2. So from here we can say this value of n theta is very large. We can say value of this n theta is very large. And for large angles, we have theta is closer to 180, and this sine of theta by 2 is going to have some finite value. Okay. And this for finite value, we can say value of our this n theta is very small. Here I missed to write one thing. Sine of theta by 2 will be approximately equal to theta by 2, and theta is close to 0. So this we can say is approximately to the maximum value, which is closer to infinity. So therefore, one second, no, my mistake, this won't work. Theta is 0, small angle, so we get this as theta by 2. So our n naught, so this n theta will be very large. Okay. And for large angle, this n theta is very small. So because of this exponential part, we are going to get, because only two possibilities are there, because when theta is closer to 0, here we are going to have maximum value, and here also we have maximum value, and when theta is on the lower side, we have a minimum value. Okay, so these 3 and 4 cannot be the correct option. Only possibility now is because of the exponential function, this graph cannot be a straight line, so option 2 is correct. Two is correct. Next question. It states that in hydrogen spectrum wavelength of first line of Balmer series, lambda is 6561 angstrom. Find out the wavelength of second line of same series in nanometer. So series is same for Balmer series, but the line is different, first and second. So we can use the Rydberg formula. And which gives us 1 upon lambda is equal to our r, and we have this as 1 upon n1 square minus 1 upon n2 square, and our value of n1 for Balmer series is fixed, that is 2. So we have our value of n1 is fixed, that is about 2, and value of n2 for first line. So we have our first line value of n2 will be equal to 3, and in this case the wavelength is given. Let us suppose that we say lambda 1 is given as 6561, and for second line value of n2 is our 4, and let us suppose the wavelength is lambda 2, which we are supposed to find out. So we can use the de-Broglie formula for our both the lines, lambda 1 as well as lambda 2. So first of all, for lambda 1 is equal to the r, and we have this as 1 square 1 upon 2 square minus 1 upon 3 square, and this comes as our, this will be 36 5 times r, and we can write now lambda 2 1 upon lambda 2 is equal to r 1 upon 2 square minus 1 upon 4 square, which will be giving us 16, and this comes as our 3 upon r. And we have to find out lambda 2. Let's take the ratio. We have lambda 2 upon lambda 1 is equal to 16 upon 3r and 36 upon 5r. r and r goes away. This can be written as 16 by 3 multiplied by 5 upon 36, and this comes as 20 upon 27. Lambda 1 we know, we can write that our lambda 2 will be equal to lambda 1 times 20 upon 27, which comes as 6561 into 20 upon 27, approximately 4855 angstrom. Okay, in nanometer, so we can say that our lambda 2 will be equal to 485.5 nanometer. So this comes as 485.5. Next question. It states that kinetic energy of a particle is E and its de-Broglie wavelength is lambda. On increasing kinetic energy by delta E, its new de-Broglie wavelength becomes lambda by 2. Then delta E is. So we start with the de-Broglie wavelength formula. So we know that our de-Broglie wavelength lambda is equal to h upon momentum p, and in terms of kinetic energy we can write that lambda is equal to h upon 2m times E, and when kinetic energy is E, the wavelength is lambda. Okay, so you can say our initial kinetic energy, which is given as E, we are having a wavelength that is our lambda, and new kinetic energy, that is our E plus delta E, our wavelength. Let us suppose that is our lambda 2, it becomes lambda by 2. So we can write that our lambda 2 will be equal to h upon 2m e plus delta e square root. Now we can just find out the ratio. We can say lambda 2 upon lambda will be equal to h upon 2m e square root and h upon 2m e plus delta e and its square root. H and h cancels out, and this 2m and 2m also cancels out. Therefore, we can write lambda 2 upon lambda will be equal to, this comes as 1 second. Oh, sorry, I've written reverse. Let me write it. This is lambda upon lambda 2. So now I can just reverse it. So this will be giving me e upon e plus delta e and whole square root. And we are given that lambda 2 is equal to lambda by 2. So therefore this will be equal to 1 by 2. Now we are going to solve it for this delta e. So if we square it, we get this as e upon e plus delta e is equal to 1 by 4. So from here we get 4 times e is equal to e plus delta e. Therefore we can say our delta e is equal to 3 times e. Delta e is 3 times e. Next question states that radiation with wavelength 6561 angstrom falls on a metal surface to produce photoelectrons. The electrons are made to enter a uniform magnetic field 3 into 10 to the minus 4 Tesla. If the radius of largest circular path followed by electrons is 10 millimeter, the work function of the metal is close to. So in this case, we start with the energy of photon, then we can make a relationship with the kinetic energy, and then we can easily for the magnetic field. So we can say that photon energy that is of EP is equal to hc upon lambda, which gives us 1240, and this is 6561, so approximately 1.89 electron volt. Now we can write the kinetic energy. Photoelectric equation which gives us that the maximum kinetic energy is equal to E photon minus work function. And we also know that electron in magnetic field, electron in a magnetic field, this will be resulting in a radius r, which is given as mass into velocity and electron multiplied by magnetic field. So this gives us that the velocity v will be equal to E multiplied by magnetic field times R and divided by mass m. So we can find out all these values. 1.6 into 10 to the power minus 19. Magnetic field is our 3 into 10 to the power minus 4. Radius is 0.01 and mass is our 9.11 into 10 to the power minus 31. So we get this velocity is approximately equal to 5.27 into 10 to the power 5 meter per second. Now we can find out the maximum kinetic energy. So we can say that our Kmax will be equal to half m v square. This comes as half into 9.11 into 10 to the power minus 31 into 5.27 into 10 to the power 5. Whole square, and this comes approximately equal to 0.79 electron volt. So we got our maximum kinetic energy as well as our photon energy we know. So we can just find out work function. So we can say that a work function phi will be equal to energy of photon minus kinetic energy maximum, which gives us 1.89 minus 0.79 approximately equal to 1.1 electron volt. Option 2 is correct. Next question. It states that the energy required to ionize a hydrogen-like ion in its ground state is 9 Rydbergs. What is the wavelength of radiation emitted when the electron in its ion jumps from second excited state to the ground state? Okay, so energy is given as 9 Rydbergs and wavelength from second to ground state. So we start with our energy for a nth level. Energy for nth level, which gives us that E of n is equal to minus z square r upon n square. And we are going to find out the ionization energy of the ground state. Okay, so we can see from here that ionization energy from ground state, that is our E ionization, will be equal to, for ground state we can put n is equal to 1 and we are only interested, that will be our magnitude, is equal to our z square times r, and we are given that this our E ionization is our 9 Rydberg. So we can say that our z square times r is equal to 9r, which gives us that z is equal to 3. Now electron in its second excited state, ground state and second excited state. Therefore we can say that for ground state, value of n is equal to 1, and second accelerated state, value of n is equal to 3. Therefore, we can say that our E of 3 is equal to minus z square r divided by 3 square, which comes as minus 9 of r upon 9, giving us minus of r. And our E of 1 will be equal to minus z square r divided by 1 square. This gives us minus of 9 times r. And we can find out the energy emitted by finding out their difference. So we can say energy of emitted photon let us call this as E, and will be equal to E1 minus E3. Let us emitted photon, let us call this as EP. So from here we get that our EP will be equal to minus of 9r and minus of minus r. This gives us minus of 8r. Now we can find out our wavelength. So we can say our wavelength is equal to lambda is equal to our hc upon energy of photon, and hc is our 1240, and energy of photon will be 8 times r. So this comes 8 multiplied by 1 r is our 13.6, and this comes as our approximately 11.4 nanometer. So option 4 is correct. Next question. It states that an electron of mass m and magnitude as E initially at rest gets accelerated by a constant electric field E. The rate of change of de-Broglie wavelength of this electron at a time t, ignoring relativistic effects. So we start with our de-Broglie wavelength and then with respect to momentum, okay, and in a constant electric field. So we can say de-Broglie wavelength lambda is equal to h upon momentum p, okay, and this is under constant electric field. Therefore we can say that for acceleration A, we can write for acceleration A, which will be equal to force divided by mass, and force is electric field multiplied by charge and they divided by mass. So from here we can write the momentum, which is our P is equal to mass into velocity, or initially it says that it was at rest. Therefore we can use the kinematic equation that V is equal to U plus AT, and here V is 0, therefore we can write V is equal to AT. So this comes as mass AT, and we substitute the value of acceleration, so we get momentum is equal to mass multiplied by mass multiplied by T. Here mass and mass cancels out, so momentum is equal to E, capital E multiplied by T. Thus we can say that our wavelength lambda will be equal to h upon E electric field and time t, and rate of change of wavelength, so we can say d lambda upon dt is equal to d of dt, and we have this as h electric field with respect to time t. This gives us minus of h upon e and t square. So this comes as minus e upon option number 1 is correct. One is correct. Next question. It states that an electron of mass m with initial velocity vector v is equal to v naught I plus v naught j in an electric field vector E minus E naught k unit vector if lambda naught is initially de-Broglie wavelength of the electron. Its de-Broglie wavelength at time t is given by. So we have to find out the wavelength, de-Broglie wavelength when it is moving in electric field E. So we are given initial velocity, that is a v is equal to v naught I plus v naught j. So we can find out its magnitude. We can write that our v will be equal to v naught square plus v naught square and its square root, giving us v naught square root by 2. And initial momentum, let us suppose that is our P is equal to m times v, okay, and this is our magnitude. So we get that our initial momentum P will be equal to m v naught square root by 2. Now from here we can find out the initial wavelength, initial de-Broglie wavelength. Initial de-Broglie wavelength, which is our lambda naught is equal to h upon p, and we can write this as h upon m v naught square root of 2. Now this moves in electric field. So next we can write motion under electric field. Motion under electric field. So the electric field is given as minus E naught k unit vector. So therefore we can say that the force, our F will be equal to minus E E naught k unit vector, and from here we can say our acceleration that is our A vector will be equal to our force oblique mass. This gives us minus E naught m upon k unit vector. So we can use the kinematics equation and write that the velocity at time t, velocity at time t can be written as v of t is equal to initial velocity is our v naught I plus v naught j, acceleration is our e naught upon m, and we have this as k unit vector multiplied by t. We can find out its magnitude. V of t is equal to v naught square plus v naught square plus e naught upon m t whole square and its square root. This comes as twice v naught square plus e naught upon m t whole square and its square root. From here we can find out the de-Broglie wavelength at time t. De-Broglie wavelength at time t. You can say that our lambda of t is equal to h upon pt, or we can say this as h upon mass v of t, and we can write this as h upon mass and square root of twice v naught square plus e naught by t, sorry, this is our e naught by m multiplied by t whole square. And we have to express it in terms of lambda naught. Okay, now it's a simple. We know that our lambda naught is equal to h upon one second. Okay, so we need to substitute h. So this is h upon m v naught square root of 2, giving us h is equal to v naught square root of 2 and multiply by m. So we can write that our lambda of t is equal to, this comes as our lambda naught v naught square root of 2 multiplied by m, and we can take m as LCM in the denominator, so m and m cancels out, so this comes as 2 m square v naught square plus e naught t whole square and its square root. And in the numerator, all the options are only in lambda naught and a constant factor. Okay, so let's take common. So this comes as m lambda naught v naught square root of 2, and we take this as m v naught as common along with square root of 2. This comes as 1 plus e square e naught square t square divided by twice m square and v naught square. So these two terms cancel out. So we cut the answer. Lambda naught 1 plus e square e naught square t square divided by twice m square v naught square and its square root. So the option 3 is correct. 3 is correct. Next question. It states that hydrogen ion and singly ionized helium atom are accelerated from rest through a same potential difference. The ratio of their final speed of hydrogen to helium ion is close to. So this is directly based on the particle accelerated by a potential difference. So we can say kinetic energy from acceleration, kinetic energy, or we can say due to potential difference, due to potential difference, we can write that our half m v square is equal to charge multiplied by potential difference. This gives us that the velocity v will be equal to 2q v divided by m and its square root. So let's define the charge and masses of hydrogen and single ionized helium. Therefore, we can say charges and the masses. So we have our hydrogen ion, H positive. This gives us that the charge is plus E and mass is, let us suppose, MP, let us suppose. Then we have singly charged helium, that is H positive. So the charge will be equal to plus E and mass will be equal to 4 times mass of the proton. Now we can easily find out their ratio of their velocities. Velocity for hydrogen and velocity for helium, single positive. This comes as twice we have charge of hydrogen, potential difference divided by mass of hydrogen, twice charge on helium, potential difference, mass of helium, square root. In this two potential difference 2 and potential difference cancels out, and from here we get this will be equal to our q upon h upon q upon he multiplied by mass of He and mass of hydrogen and its square root. Simply substitute the values. Both are having charge as E. Mass of helium is 4 times mass of proton, and this is mass of proton and its square root. So this cancels out. and this comes as our square root of 4, which is 2 is to 1. So option number 1 is correct. Option 1 is correct. So this completes part 1 of year 2020, or we can say 2020, 31 questions. Next part we are going to solve some more questions for the 2020. Thank you.